Okay, so today we're going to look at factoring special cases. These are special patterns that we need to look for in order to make our factoring of them easier. Okay. A lot of these you can factor using the old methods like product sum, but if you can recognize the patterns, it's going to make things a lot easier. Okay. So there's two main ones that we're going to do, and then we're going to mix and match them at the end. The first special pattern is called a difference of squares, or I was abbreviated at DOS. Difference of squares. In a difference of squares special pattern, we're looking for three things. Okay. We're looking for if there's two terms. Okay. Now everything we've factored so far, most of what we've factored so far, have been trinomials. Difference of squares is the technique you want to use if there's only two terms. Okay, it's a binomial. So if there are two terms, then you could potentially use the difference of squares pattern. So that's the first question you have to ask. Second question you have to ask is, are both the terms perfect squares? Are both terms perfect squares? Okay. If they are, and there's also two terms, then you could potentially use difference of squares pattern. And the last thing you have to ask is the difference of squares. Difference means subtracting. Are you subtracting those two terms? Okay. And if you are, and you answer yes to all three of these questions, then it is a difference of squares pattern. Okay. So if there's two terms, okay, if there's two terms, again, right now the only thing we know for two terms is you look for a GCF. So now if there's two terms, always look for a GCF, but then also see if it is a difference of squares pattern. So are there two terms? Are they both perfect squares? Are you subtracting them? If you answer yes to all three of these, then you could use the difference of squares pattern. And difference of squares pattern is if you have a squared, so you're minus b squared. So if your problem is set up like this and it tells you to factor, okay, so let's look at what we have. We have two terms. We have an a squared and we have a b squared. They're both perfect squares. Okay, a squared is a perfect square, b squared is a perfect square, b times b, a times a, and they're being subtracted. Now again, for your numbers perfect squares, those are things like 2 squared is 4, 3 squared is 9, 16, 25, 36. Any whole number squared is a perfect square, and then any variable raised to an even power is also a perfect square. So I'm actually going to add that up here. So any even exponent or whole number squared. Alright, so back to the pattern. A squared minus b squared. If, again, it answers yes to all three of those questions, two terms, both perfect squares, subtracting. If that's the case, then your factored pattern is going to be two binomials multiplied together. One's a plus, one's a minus. And then you do the square root of the first term in the first slot, and the square root of the second term in the second slot. Okay. So the square root of a squared is a. So a is going to go in the first slots. Square root of b squared is b. B times b is b squared, a times a is a squared. Those are the square roots. That goes in the second slot. So your factored form of a difference of squares is always the exact same terms with opposite signs. So a plus b times a minus b. And when we're doing FOIL, we've seen this pattern before where the inside and the outside terms cancel out. All right, let's look at one with some basic numbers in it. Let's say we have, because again, we don't normally see a squared minus b squared. We'll see something like x squared minus 9. Okay. Run through the three questions. Are there two terms in this? Yeah, there are. You got x squared and 9. Are they both perfect squares? Yeah, x squared is x times x. 9 is 3 times 3. And are you subtracting them? Yeah, there's a minus sign in there. So when we factor it, again, always going to be two binomials. One's plus, one's minus. And then the first term is the square root of the first. So we said x times x is x squared. And we said 3 times 3 is 9. So x plus 3x minus 3. And that's factored. Okay. Now how can you use product sum with that? Well, again, product sums for trinomials, and technically our middle term in these binomials are 0. So another way to think of it is what multiplies to -9 and adds to 0. Well, it has to be the same number for that to happen with opposite signs, so -3, +3. But again, if you could recognize the patterns, and you should be able to recognize the patterns, it's a lot easier to just see the difference of squares. Okay, let's look at a couple more with the numbers in. Alright, this first one, x squared minus 16. X squared is a perfect square, 16 is a perfect square. X squared is x, 16 is 4 times 4. So our factored form is going to be x plus 4 times x minus 4. And that's factored. Again, you could do a quick FOIL and make sure you get the same answer. If you have the same terms, opposite signs, inside and outside will cancel out, and you'll be left with the original problem. Alright, the second one, this one's a little weirder. Not a normal format. But again, when we're looking for perfect squares, we're looking for a whole number squared or an even exponent on a variable. Okay. So the second one, 9x squared minus 25y squared, two terms, subtracting, are they both perfect squares? Well, yeah. 3x times 3x is 3x squared, and 5y times 5y is 25y squared. So in our factored form, we're going to have 3x plus 5y times 3x minus 5y. So same terms, opposite signs, one of each. Alright, and then the last one, x squared plus 100. Run through the questions. Are there two terms? Yes, x squared and 100. Are they both perfect squares? Yes. X times x is x squared. 10 times 10 is 100. Are you subtracting? No, you're not. This is not a difference of squares. Okay. So it looks like it's the same pattern, but it is, again, it has to be a difference. It has to be a subtraction. So this one's actually prime. It's not factorable. Just make sure when you're using the pattern, make sure it actually follows the pattern. So that's a special pattern for two terms, difference of squares. So if you only have two terms, first look for a GCF. Second, see if it's a difference of squares. The second special case is called a perfect square trinomial. We've talked about this a little bit as well. Perfect square trinomial comes from one binomial squared. Okay, but again, we're going to be going backwards when we factor. Alright, so a perfect square trinomial, or PST. So trinomials in the word, perfect squares in the word. So we're going to be dealing with perfect squares again, and we're going to be dealing with trinomials. So anytime you do have a trinomial, you should always check product sum. A lot of these you could also factor using product sum. But again, if you could recognize the pattern, it's going to make things easier. And this pattern comes up a lot in algebra. Alright, so in a perfect square trinomial, we're also going to ask ourselves three questions. There's going to be three terms in a trinomial, and we have to ask if the first term is a perfect square. So same rules apply, even exponent and or a whole number squared. So is the first term a perfect square? If yes, you could keep going. Second question, is the last term a perfect square? So again, we're going to have three terms here. The first one's a perfect square and the last one's a perfect square. Keep going. Okay, so before we go to the third one, I'm going to assign variables to these first ones. So is the first term a perfect square, meaning it's something like some value a to the second power. And is your second term, or is your last term a perfect square? Say it's something like b to the second power. Okay. Now what we're looking for in the third question, okay, again, if the first term is perfect square, the last term is perfect square, move on to the third question. We're looking at the middle term is twice the product of a and b. Twice the product of a times b. Alright, well, what are a and b? A is the square root of the first term. B is the square root of the second term. You multiply them together and then double it. Okay. So this one's a lot easier to see in the examples, but first we'll write down the pattern. The pattern being, if you have a squared plus 2ab plus b squared. Okay, so this is the pattern involving the a's and the b's. So a squared plus 2ab plus b squared. This will be the trinomial form that you're going to be given to factor. So run through the questions. Is the first term a perfect square? Yes, it is. A times A is A squared. Is the second term a perfect square? Or is the last term a perfect square, rather? Yeah, B times B is B squared. Is the middle term the product, twice the product of A times B? Okay. Twice the product of A times B. The product of A times B is A times B. Twice of it would be 2AB. Okay. Well, A times B, double it is 2AB. So what form do we have? What's the pattern for these? Well, it's always going to be one binomial squared. Okay. And that binomial is going to be the square root of the first term, which is A, the square root of the last term, keep saying second, which is B, and then whatever sign was in the middle. Okay. So in this case, it was plus 2AB. So the sign in the middle is plus. A plus B to the second power foils out to A squared plus 2AB plus B squared. Okay. So again, we said a binomial squared is not the square of both terms. You do have to FOIL it. So if you're going backwards, you're going to have to use FOIL. Okay. So that's the main pattern. And then real quick, we'll do the second one, which is the exact same thing except a minus in the middle. If you have A squared minus 2AB plus B squared as your pattern, that's simply going to factor into A minus B to the second power. Okay, so again, whatever sign is in the middle goes in the middle in your factored form. Alright, so like I said, this one's a little harder to see with just the variables. So let's look at some ones with numbers in them. Alright, so this first example, x squared minus 16x plus 64. Okay. Run through your questions. Is the first term a perfect square? Yes. X times x is x to the second power. Is the last term a perfect square? Yes. 8 times 8 is 64. Okay, so now we have the two square roots. We got A and we got B. X is A, B is 8. Multiply them together. Okay, the product. X times 8 is 8x. Okay. Double it. Double 8x is 16x. 16x is in the middle. So this is a perfect square trinomial. So we take whatever sign is in the middle, which is minus, and then we square the whole thing. And that is factored. Let's look at the next one. 9x squared plus 12x plus 4. Okay. Now again, both of these you could factor using our other techniques. Okay, but again, recognizing the pattern. So on the first one, going back to the first one, if we were just using product sum, we'd think, all right, what multiplies to 64 and adds to negative 16? It'd be negative 8 and negative 8. That one's a little easier to do product sum. So if you can't recognize the pattern, you can always just factor it normally. This one, you can't do product sum. You'd have to use guess and check or one of the other methods. So 9x squared plus 12x plus 4. Well, let's see if it's a perfect square trinomial. Okay. Is the first term a perfect square? Yes. 3x times 3x is 3x squared. Is the last term a perfect square? Yes. Last term is 4. 2 times 2 is 4. Okay. Once you have those two terms together, multiply them together. 3x times 2 is 6x. Double it, you get 12x, which is the middle term. Okay. So that means it is a perfect square trinomial. We'll take the sign in the middle, and we'll square the whole thing. So again, factoring that one using one of the other methods would be very difficult. Okay, but factoring it, if you could recognize the pattern, it becomes a lot easier. Alright, and this last one, this would be terrible to factor using the other methods like guess check. So instead, recognize that, hey, some of these numbers are perfect squares. We got 25 in front, we got 121 at the end. Those are both perfect squares. So check to see if it's a perfect square trinomial. Alright, so I would start with the first term. Is the first term a perfect square? Yes. 25x squared is 5x times 5x. The last term, 121y squared. Is that a perfect square? And yes, it is. 11 times 11 is 121. Y times y is y squared. So 11y times 11y would be 121 squared. Multiply those two together. So multiply 5x plus 11y, or 5x times 11y, which would be 55xy. Double it. 55 doubled is 110, and that is the middle term. So what we do is we take the sign in the middle, and put it between our two, and then square the whole thing. And again, what this means is that if you do 5x minus 11y times 5x minus 11y, you're going to end up with the trinomial that we started with. Okay, so a couple quick things to note when we're dealing with perfect square trinomials. If we scroll up to the pattern here, notice that both of the b squared terms are positive. So to be a perfect square trinomial, both of the last terms have to be positive. Okay, it has to be plus the constant, or plus whatever b squared is. The other thing notice is that you have to do that middle term. So it's not just everything that has a perfect square first term and perfect square last term doesn't necessarily mean that it's going to be a perfect square trinomial. So you do always have to ask the last question, which is if the middle term is twice the product of a and b, so twice the product of those first two square roots. Okay. Because not you could answer yes to the first two questions, and if the last one's no, then it's not a perfect square trinomial. Which is actually what this first question is, or this last example is. So if we're looking at this is a trinomial. X squared, the first term, is a perfect square. The last term, 36, is a perfect square, 6 times 6. Okay. Multiply those together. X times 6 is 6x. Double it, and you get 12x. Okay. We don't need 12x. We want 13x. Okay. This one's not a perfect square trinomial. So just because it looks like a perfect square trinomial doesn't mean it is a perfect square trinomial. You do have to ask and answer all three questions. Okay, so since this is not a perfect square trinomial, we can't factor it using the perfect square trinomial pattern. So we have to go back to one of our other patterns, or one of our other methods, such as product sum. So this one is factorable, but it's not factorable using a special pattern. Okay. Product sum, we'd be looking for two numbers that multiply to 36 and add to 13. What multiplies to 36 and adds to 13? Well, again, you could run through all the numbers that multiply to 36. 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6. Okay. Which of those multiply? Well, they all multiply to 36. Which of them add to 13? Well, it's going to be 4 and 9. So our factored form would be x plus 4 times x plus 9. So not everything's a special pattern, even though it might look like a special pattern. You always have to ask yourself the three questions and check. All right, and then the last thing we're going to talk about is multiple factors. When we're factoring a problem, or a lot of times the directions will say factor completely. Factoring completely means you keep factoring until nothing else is factorable. So you factor until you can't factor anymore. And one hint for a lot of these is to always look for a greatest common factor. The greatest common factor is kind of step 0. It's what you want to look for before you start any factoring problem. So let's look at a couple that have multiple factoring techniques. Okay, so this first example, 12x squared minus 12x plus 3. Okay, it's a trinomial, so we could try one of our other trinomial methods. But before we try those, we should recognize that, look at our numbers. We have 12, 12, and 3. 12, 12, and 3 all have a common factor, greatest common factor of 3. So the first thing we're going to do to try and factor this problem is to factor out the greatest common factor of 3. So you take out the 3. What's left behind, after you divide each term by 3, you're going to be left with 4x squared minus 4x plus 1. All right, so we factored it once, but we want to factor it completely. So we have to check if it's still factorable. And this one is. We can still factor this because 4x squared minus 4x plus 1 is a perfect square trinomial. How do I know it's a perfect square trinomial? Well, the first term is a perfect square. 4x squared is 2x. 2x times 2x. The last term is also a perfect square. 1 times 1 is 1. If I multiply those two together and double it, I'll get this middle term. 2x times 1 is 2x. 2x doubled is 4x. This is a perfect square trinomial. So my fully factored form is going to have the GCF out front, and then the perfect square trinomial factor next. So it's going to be 2x from the first term, the 1 from the last term, the sign from the middle, and then don't forget to square that whole thing. All right, so again, if we didn't do the GCF, that isn't a perfect square trinomial. So always look for a greatest common factor and then see if it's a special pattern or see if it's factorable again. Second one, two terms. Two difference of squares. See if it's different squares. There are two terms, but they're not both perfect squares. 45 is not a perfect square and 20 is not a perfect square. Okay? So this isn't a difference of squares pattern. But we didn't do step 0. We didn't do the first thing you always want to do in a factoring problem. You always want to look for a greatest common factor. And this one does have a greatest common factor. There's two terms here. The biggest number that goes into 45 and 20 is 5. And the most x's we could take out is x squared. We could take 2 from each. So what's left over when we factor out the greatest common factor of 5x squared? We're left with 9 minus 4x squared. Okay? Divide each number by 5, take away 2 x's. Alright, well, now I'm left with a binomial, two terms. Both are perfect squares, and we are subtracting them, which means 9 minus 4x squared is a difference of squares. Which means we should factor it using the difference of squares factoring pattern. So the GCF is going to stay out front. And since it's a difference of squares, we're going to have two binomials. One's plus, one's minus. The square root of 9 is 3. So 3 is going to go in the first slots. And the square root of 4x squared is 2x. So 2x will go in the second slots. That is our factored form. GCF out front, difference of squares pattern inside. All right, then the very last one we're going to talk about, x to the fourth minus 16. Okay, this one seems easy. And it is easy. First, let's look for a greatest common factor. Okay, there isn't one. First term doesn't have a number in front. The second term doesn't have a variable. So there's no greatest common factor here. All right, well, there are only two terms, which means our trinomial techniques aren't going to work here. So the only other two-term method that we have right now is a difference of squares. Is this a difference of squares? And yeah, it is. The first term is a perfect square. Okay. X to the fourth power is x squared times x squared. Remember, any exponent with an even power is a perfect square. And then 16 is 4 times 4. So the first factored form for this is going to be x squared plus 4 times x squared minus 4. Okay. So this looks like it's in factored form now. The problem is it is factored, but it's not factored completely. Okay. We still have two binomials here. X squared plus 4 is a binomial. It's not a difference of squares, though, because you're not subtracting. However, x squared minus 4 is a difference of squares. X squared is a perfect square, 4 is a perfect square. So we could factor that one even more. It's going to be x plus 2 times x minus 2. And then the first one is going to just stay the same because x squared plus 4 is prime. So this one is our completely factored form. So that one had a double difference of squares. It had two difference of squares. The first, we did difference of squares in the first step, and we did difference of squares in the second step. So you always want to keep checking after you factor it once. See if you could factor it again. Sometimes you can, a lot of times you can't, but you always want to check. And like I said, knowing these special patterns is going to make things a lot easier for us. And they're all just, each one's just 3 questions. Perfect square trinomials, first term perfect square, last term perfect square, and then make sure to check the middle term is twice the product of A and B. And difference of squares, 3 simple questions. Two terms, are they both perfect squares? Are you subtracting? If you are, then you could use the perfect square, or the difference of squares pattern of a plus b times a minus